Maybe so we're going to get started with our next speaker. So we have Giulia Semeghini here from Harvard. She's an assistant professor of applied physics in the School of Engineering. And today she'll be talking about her neutral atom arrays. So welcome.
Thank you so much. Hopefully everybody can hear me. Please ask me questions throughout the talk. Today I'm going to talk to you about a new atom array platform that we are developing at Harvard. Since we're building it, you're going to see some fancy pictures of the experimental setup that we're building. Not a lot of experimental results yet, but I'm going to show you some past results that we're trying to build on and trying to give you the motivation of the work that we're doing and what are the applications that we're thinking about. So just to give you some context, as you probably all know, this platform that is based on atom arrays has, in the past, let's say, almost 10 years now, developed into a pretty powerful quantum computing platform where different kinds of applications have been explored, ranging from quantum simulation to quantum computing in a stricter sense, to also applications in quantum metrology. And, I think for us in this community that there has been quite a lot of excitement excuse me, in the capabilities that this platform has been able to develop. In a sense, this makes, it's the moment where things need to get serious, right? We've been able to demonstrate some very cool applications, but now we really want to make those next steps that would allow us to get to some really useful and exciting applications. And so this means that we need to work on two parallel directions. On one side, we need to improve even further the technical capabilities that we have. And there are some outstanding challenges that we need to face, from the number of qubits to the fidelities and robustness to noise and imperfections. But also we need to, at the same time, think about how we can implement useful applications, both in terms of simulations that are interesting for fundamental science, but also algorithms that can be useful for many different purposes. And as we do this, this is now maybe an overused term, but still I think it kind of works describing what we would like to do. We really need to do these two things together. And I think this is really the spirit that we're using while developing this new platform. We need to think, what are the applications that we want to enable, and so what are the capabilities that we need to get there, and vice versa. So in this talk, I will briefly go over the key ingredients of atom arrays. Maybe all of you are already familiar with it, but just to be sure that everybody knows what we're talking about, I will go over some recent results in quantum error correction using this platform, and then I will try to spend most of the talk telling you about what are the new possibilities that we see could be enabled by a new type of atom array that uses two atomic species. So just going over this quick introduction, what do these atom arrays look like? So we take neutral atoms and we trap them individually into these optical tweezers, which are simply tightly focused laser beams that can trap just one atom inside. And then we create two-dimensional arrays of these tweezers to trap atoms into them. So the way this works is you have this cold cloud of atoms, you shine the tweezers on top of that cloud, you start loading the atoms at the beginning in a stochastic way. So you have about 50% of your traps loaded with atoms. You would like to create some defect-free array, and so the way we do it is we use this a second set of optical tweezers to move the atoms around. And so you can pick up an atom and move it across the array and drop it off at the location where you would like to have a field trap. And so by doing this, you can achieve what you see there on the right, which is an array with about 300 atoms, which is almost defect-free. We can get to about 99% filling. This just for the experimentalists, this strongly depends on the vacuum lifetime of your system. So it can go as close as possible to 100% with better vacuum lifetimes. So, so here is the first key ingredient of this platform. We can create defect-free arrays of atoms in two-dimensional arrays with programmable geometries. Because the way this works, you can really change the geometry from a square lattice to honeycomb to Kagome to whatever you want to do just in a few seconds by changing a few lines of code. The second ingredient is how do we achieve strong interactions between the atoms. As I mentioned, these are neutral atoms. Those atoms up there in those arrays are a few microns away from each other, so they don't naturally interact. So we need to do something to have them talk to each other. And we do this by exciting them to a Rydberg state. So you start with your atom in the ground state, you promote one of its valence electrons to a Rydberg state, which is simply a highly excited electronic state, such that you have an electron that is far away from the nucleus, and so you have a strong dipole in your atom. And so if you have two dipoles, they interact with each other through van der Waals interactions. The mechanism that we're gonna use a lot is the so-called Rydberg blockade, which simply tells you that if you have two atoms somewhere close to each other and you apply this, you have this optical transition that couples the ground to the Rydberg state. If the two atoms are far enough from each other, then you can promote one or both of them to the Rydberg state. But if you put them close, then you have this energy shift on the doubly excited state that prevents you from exciting both of them to the Rydberg state within a certain distance. So you have a blockade radius within which you cannot excite, I'm sorry, more than one atom to the Rydberg state at a time. And this Rydberg blockade effect is what we're going to use to generate entanglement, both when we do analog dynamics in quantum simulation or when we perform entangling gates, for example. So these are just the basics. If you have any questions here, please let me know. I went fairly quickly because I think many of you have already seen this. So the next thing I want to show you is kind of to catch up on what is the state of the art with this platform. And so showing you some recent results that have been achieved in performing quantum error correction with atom arrays. And these results that I'm going to show you have been achieved in the Looking group at Harvard, where I did my postdoc. And here we use a single species atom array with rubidium atoms. So let me just quickly show you the people that have been involved in these experiments that I'm going to briefly show you. So here below is the experimental group, and up here some of the many theory collaborators that I worked with us on this. So the one key ingredient that these atom arrays have that I think make quantum circuits interestingly efficient is this idea of reconfigurable connectivity that I'm going to show you in a second. But before we get there, we want to see how we can implement quantum error correction. And you know that when you want to implement quantum error correction, you want to have your information stored non-locally in some entangled many-body system. And so you want to be able to generate logical qubits. And we can take, for example, the toric code. So you have this graph of atoms that need to be entangled with each other according to a certain pattern. And I want to show you how this can be done quite efficiently using this idea of reconfigurable connectivity. So the way we did this in our lab in 2022 was to use the following scheme. So we have, I lost my pointer. Oh, there you go. So we have these black atoms here. They correspond to our data qubits in the surface code, and then we add a few ancilla qubits at the center of the plaquettes of the toric code. And we use the ancilla qubit to mediate entanglement between the data qubits in the following way. As you can see here, what we do is we keep the data qubits static in place, and we move the ancilla qubits around to achieve a sequence of 2 qubit entangling gates. So what you see here is we place, and this is done by these Rydberg-mediated interactions. So we put the ancilla qubit next to the first data qubit, we perform an entangling gate, then we move it close to another one, second entangling gate, and so on. And I can show you how this works, show showing you this video. So here, the atoms that you see that just stay in place are, again, the data qubits, and you see these ancilla qubits moving around to mediate the interactions. And every time you see one of these red circles is because there is an entangling gate happening. So what we do is we have a big laser beam that performs this excitation to the Rydberg state that covers the whole array. And so interactions only happen when the atoms are close to each other. So we use, so when they are at this distance that you see here, they're not interacting, but when we put them closer, as you see in the video, then every time we shine this Rydberg laser, there is an entangling gate happening. And so this idea of moving the atoms around throughout the circuit allow us to have efficient circuits because we're basically rewiring our atom array at each step of the circuit, right? Two atoms are connected to each other, and then they get disconnected and connected to something else by using these atom transports. So this was used, so this can be used, as you see here, to change the connectivity, but it can also be used to perform logical gates in a very simple way. So let's say that we initialize two logical qubits in this way, and then we want to perform, let's say, a CNOT gate between them. The way we do this is, okay, we encode the two logical qubits, and then we overlap them. So we transport one of the two logical qubits right next to the other one, so that the twin atoms in each logical qubit sit next to each other, so that when we apply our Rydberg gate, then the two atoms sitting next to each other are going to undergo a CNOT gate, which corresponds to a transversal CNOT gate for the two logical qubits. And this means that we just need this global move of the whole logical qubit on top of the other one, and one pulse of this Rydberg laser to perform this logical CNOT gate. So here, just showing you again, and one thing that you want to see here, so again, here we have our two surface code logical qubits, and what we do is, again, overlap the two of them to implement this CNOT gate, and we can change the distance of the surface code, so the size of these logical qubits, to see how the performance changes for larger system sizes. And so here in this experiment from 2024, we probed these two code distances, and importantly, we saw that the performance, like the fidelity of this CNOT gate, of this logical CNOT gate, improved by improving the surface code distance, which is what is supposed to happen if this quantum error correction is working properly. Okay, so the last thing I want to show you is, again, here I'm going very quickly, just showing you a few highlights of this paper that is very long and has a lot of things into it, just to show you how we are using these atom arrays to perform these kind of operations. And the last thing I want to mention is how we perform circuits using this so-called zoned architecture. So what we do here is we have separate zones where different kinds of operations happen. So we have an entangling zone here at the center where, you know, the most interesting things happen. So this is where we have this Rydberg laser beam that is used to perform entangling gates. Then we have a storage zone up here where the atoms can either just stand idle. So here there is no entangling laser beam, so there can be no entangling gate. Here we can only have the atoms in idling mode, or we can perform logical one qubit gates. So we have some localized laser beams that can perform just single qubit operations. And finally, we have this readout zone here at the bottom where we move the atoms out to perform the readout of a subset of qubits. So this is far enough such that if you perform fluorescence imaging on these atoms here, you have no interference with the atoms in the first two zones. Okay, so last thing, I'm going to show you another video that kind of gives you the idea of how this platform operates when we implement these logical circuits. So here, you know, what we're doing is not too important. Here we're encoding our logical qubits using these 3D code blocks. And so here you see these 8 atoms are gonna form one logical qubit, and we're gonna have a few. And you're gonna see like how the operations work. So here you see at the beginning, we are encoding the logical qubits in these code blocks. So there are some local operations, and then we start performing logical gates. So you see how the atoms are moving long distances because we're performing these transversal gates by overlapping logical qubits with each other, and we swap the atoms in and out from the storage zone to select which atoms are gonna perform entangling operations and which are gonna stay IO here in the storage area. Okay. So with this, I will conclude this first part. I just want to mention here, you know, what is still quite impressive to me is that we're now already able to perform circuits with a fairly large number of logical qubits, up to 48. And these are already fairly serious logical algorithms, but of course we would like to do even better. And so this is gonna be the last part of my talk. Again, if there are questions here, happy to stop. Yeah.
How often will an atom get lost in a tweezer array? And is there a way to detect in the middle of a circuit?
Sorry, can you say it again?
How often will an atom get lost in the tweezer array? And is there a way to detect it in the middle of your circuit?
Yeah, so this is one of the things I'm going to talk about in this last part. So I'm going to answer that question. Yeah.
Thank you.
Anything else here? Okay. Yeah.
How significant is the idling noise in your storage zone?
So, so one thing that you have is just losses. So the atom can be, you know, can just be kicked out of the trap. Other than that, you know, you can have some. So you have your atoms in these optical tweezers, and if they are in some superposition state, if you have some phase noise, for example, in your trap, you can have some dephasing happening to your atom. So it depends on a bunch of things. For this experiment in particular, where we use rubidium, you're sensitive to differential light shifts between the 2 qubit states. So that's, for example, one source of the coherence. Other than that, not much. So in this idling zone, we also do single qubit gates. So those can have some errors. But if they're just sitting there, I would say it's mainly losses and these local light shifts that introduce dephasing. Yeah. But right now, we can keep them there for you know, seconds without too much problem. Okay. Yeah.
So regarding this large-scale logical algorithm run under this.
Sorry, I cannot hear you at all.
So you mentioned you can run like 48 actual largest logical. But if I understand correctly, there's actually error correction is not happening yet. So I'm just wondering that are there already some advantage by just encoding your qubits into some logical block and running the native algorithm without correcting?
Yeah, so in that paper, we were only doing error detection. So we were implementing these circuits and just keeping track of errors. So we were doing some mid-circuit readout and keeping track of the errors that we detected. The most recent set of experiments that are going to be published soon, I think, also do error correction. There is some, you know, there is some advantage already in detecting the errors because, you know, if you just keep track of what's happening, you see an improvement of the performances if you you know, if you post-select or just correct the results, taking into account what were the errors that occurred. Of course, if you do error correction, you can get even better, depending on the performances of your, you know, circuit readout and feedback that you apply to your system. But yeah, so there is more coming soon. But in this paper, just error detection already improved things. I showed you, for example, the performance of this CNOT gate. This was done just by using error detection. Yeah. Okay, so let me quickly move on to this last part. So as I said, you know, exciting things already happening. I just want to show you what we would like to achieve by building this new type of platform that uses 2 atomic species, and in particular, it uses ytterbium and rubidium atoms, and also combines this with these fast atom reloading, which is related to the first questions before. So the idea is you have this atom array with the two species, and you want to have a reservoir of atoms where you can pick up atoms and replenish any lost atoms that you have in your main array very quickly. So I'm going to talk about that in a second. So, but these are the two key elements of this platform. So again, as I said at the beginning, what we're trying to do here is really to push the technical capabilities and introduce specific ones that could enable new applications that we care about. So what we are trying to do here is really to combine the scalability that comes from this fast atom reloading with the versatility that is given by the combination of these two atomic species. And in our vision, we have two goals. One is, in the near term, we think that this versatility can really allow us to have resource-efficient approaches to quantum computing and simulation. But also, we would like to think a little bit more in the long term and try to test and compare different strategies and architectures that should enable fault-tolerant operations. So let me give you some more details. So as I mentioned, we are using these two atomic species. Why is it worth introducing two atomic species? And if you're in the lab, this is a question that you're going to ask yourselves a lot of times, because two species means a lot of lasers, a lot of work. So the reasons are two. The first one is if you have two atomic species, then you have spectral separation between them, which means that you can control them and read them out selectively. So we talked about before data and ancilla qubits. These before were the same types of atoms. And if you wanted to do any selective control, you had to be clever with like either local controls or moving the atoms away to do selective operations. In this case, because they're just two different atoms that have different resonances, you can control them very easily and in an independent way. And the other thing is you now have three types of interactions that you can tune and that can give you additional versatility for quantum architectures, as we're going to see in a second, because you have both interspecies and intraspecies interactions. In particular, we decided to use these two atomic species, ytterbium and rubidium, because this gives you a combination of alkali and alkaline earth atoms that have complementary features that can be used, again, to maximize the efficiency of this platform. So rubidium is, AIMO physicists' favorite atom because it's just very simple. It's a very well-developed toolbox. It's easy to use, and it works pretty well. A lot of the results that have been achieved so far with atom arrays have been achieved using rubidium atoms. But at the same time, ytterbium has quite a few interesting additional features that you can use. You have a nuclear spin qubit that has longer coherence times because it's insensitive to most of the noise that affects the hyperfine qubits in rubidium. You have these metastable states that you can use for different types of applications. You can trap the atoms while they're in the Rydberg state. So again, this gives rise to longer coherence times and longer interrogation times. So there are a few tools here that are very interesting. And what we're hoping to do is really to combine these two atoms to get the best of the two worlds and to use each atom for the role that is best suited to it. And the other element that I mentioned is that we want to implement fast continuous atom reloading. How does this look like? So what we're trying to do is to compensate for atom losses, for atom losses to improve the scalability. And this, and so maybe I didn't put in the slide, but to answer the question before, there are two types of losses that happen here. Okay, good. There are two types of losses that happen here. One is just related to the vacuum lifetime. So everything happens in ultra high vacuum, but of course you have some, some extra molecules and atoms that are flying around, and this can kick out the atom from its trap. This happens on pretty long time scales. So the vacuum lifetime can be, from tens of seconds to a few minutes, depending on the level of vacuum. So that happens on a low time scale. I think the one that hits you the most is when you image your atoms, you typically have a fairly destructive imaging because you're just doing fluorescence imaging. And so that one can just heat up the atoms out of the trap. So when you want to do error correction, so you want to be able to do mid-circuit readouts, you need to take into account that you're going to lose some of your atoms through that mechanism. So if we want to be able to compensate for losses on fast timescales and to have continuous operations, what we want to do is to have in parallel the possibility to do atom cooling and loading and quantum operations on the other side. So the way we do this is we have one region of our experiment where we initialize the atoms in a MOT, and then another region where we have our science array where we do the quantum operations. And we connect these two with an optical lattice. It's a running wave optical lattice, so we can load the atoms into the lattice and then shift the interference pattern to move the atoms on the other side, and this can be done fairly quickly on the order of tens of milliseconds. Once the atoms arrive in this second area, we can pull them out of the lattice and then put them into a reservoir that is located right next to our science array, such that anytime we need these new fresh atoms, we can pick them up and put them into the array. And we can do this, as I mentioned, we can do this in parallel, and so we can create a conveyor belt sequence where on one side we keep loading the atoms into the MOT and taking them into the second part of the vacuum chamber while the quantum operations are happening. Because here, everything that happens in the MOT cannot affect what happens in the science array because they're just partially separated. Okay, so this is the idea. And with this, what we are hoping to achieve is, on one side, improve scalability. Again, you're not limited by, for example, vacuum lifetime. We are hoping to achieve faster cycle times. If this works as we hope, we should be able to get cycle times of like 20, 30 milliseconds, which is a 10 times improvement with respect to current cycle times. And also, since we can replace atoms after mid-circuit readout, we can also have much deeper circuits because we don't have a limit that is given by the number of oscilla qubits that you have in your system. Okay, so where are we now? So since I started as a faculty at Harvard about 2 years ago, we designed this fairly complicated vacuum system. We built it, and a few months ago, we achieved the MOTs for both atoms. And just yesterday, we started loading atoms into this transport lattice. So this is the first image that we have of atoms in the lattice. So we are now working on this transport sequence. So hopefully, atoms in the tweezers sometime in the summer. So now I want to tell you a little bit about what are the tools that we're hoping to implement with this platform. So the first thing that I already kind of mentioned is to have fast and low crosstalk mid-circuit readout. So since you have two atoms with different, there is a spectral separation between the two atoms. When you image one of the two atoms, the other one is not going to be affected at all. So we can do mid-circuit readouts just in situ, right? So if one of the two atoms represents the ancilla qubits, you can just image them without perturbing the information that is stored in the other atomic species. One of the things that we're really excited about trying is to implement multi-qubit gates. So this would allow us to have faster and more efficient circuits. So the idea, for example, let's take again our friend, the surface code. And again, we have data qubits here are the purple ones, and ancilla qubits in green. So instead of doing what we did before, like a sequence of 2-qubit gates, what we would like to do to have a more efficient circuit is, for example, to apply a 5-qubit gate that can entangle all the atoms in a plaquette at the same time. To do this with these Rydberg atoms, you would like to have asymmetric interaction. So basically, you have this entangling gate where the ancilla qubit in the middle can allow you to perform a controlled operation on the 4 data qubits around it. And so there is a scheme for which you can do this if you're able to independently tune the interactions between control and target qubits independently. On top of this, what we can do is if we only want to apply these gates on some of these plaquettes at a given time, we can apply some local light shifts on the ancilla qubits at the center of the plaquettes where you don't want the entangling gate to happen, to just tune them out of resonance of their Rydberg interaction, which allows you to have a very fast switch on and off of the entangling gate. So instead of moving the atoms as we were doing before, so using distance as the control parameter for interactions being on and off, here we can just tune out of resonance some of these ancilla qubits such that the entangling gate would not happen. And here we just look at the specific interaction strengths that we can achieve with our atoms to verify that this can happen as we hope. So we can have strong interactions between the two species, but very low interactions between atoms of the same species. So I'm going fast, but maybe I can answer questions later. So the first thing that we would like to achieve with this is to speed up our quantum circuit. So just a quick comparison between how you would do the same thing. So for example, measure or initialize your surface code stabilizer in a single species experiment versus a mixed species experiment. So here is the same thing that I showed you before, where you initialize the stabilizer by doing a sequence of 2 qubit gates and interlaid by moving the atoms around to put them close to each other in pairs. And so here, the main limitation on time is really the movement. It takes a few hundred of microseconds to move the atoms around, even on short distances. Whereas in our case, we don't need to move the atoms at all, and we can just perform these entangling gates in one single operation. And so here you have something, on top you have something of the order of a millisecond or so, and here below you just have the time of your entangling gate that is hundreds of nanoseconds. So this just show you that if we're able to perform these multi-qubit gates with the same, with comparable fidelities as these 2 qubit gates, we can have a serious improvement of the circuit time. And this becomes even more crucial if you're implementing error-correcting codes that are a bit more complicated than the surface code. For example, if you look into high-dimensional error-correcting codes that have high-weight stabilizers. And so being able to apply multi-qubit gates becomes even more crucial. So I think I'm out of time. So let me just mention 2 quick things so that maybe we can talk with interested people later. So one other thing that we would like to do is to, instead of just doing these coherent dynamics that we're used to when doing quantum error correction, we would like to probe if we can use one of the 2 atomic species actually as a dissipative bath. So having one of the species being our system and having a coherent coupling with a bath where we can introduce dissipation by, for example, introducing optical pumping into the atoms of the bath. And this can be used to do state preparation, cooling, and even passive error correction. And these are, for example, these are ideas that have been recently probed in this experiment by Google. Let me just quickly mention the last thing. We really like the versatility that this platform gives us because we have these 2 atoms that have these different properties. And so it allows us to probe different kinds of encoding of the degrees of freedom, including different types of qubits, but also qubits. We can also use the quantum statistics of the atoms to do something interesting. And on top of that, as I mentioned, we have these 3 types of interactions that we can tune to do something interesting in terms of quantum simulation. And just to give you an idea, we're thinking about different approaches to simulate lattice gauge theories that include analog implementations that are a bit more simpler. You use the 2 atoms to encode the 2 different degrees of freedom that are matter fields and gauge fields. But also there's something a bit more ambitious, I would say, where you have a digital kind of quantum simulation and you use the fermionic atoms to encode your fermions, so the matter degrees of freedom in your lattice gauge theory, and other atoms to encode the gauge fields. You can use qubits. You know, there's a whole world there that I'd be happy to talk about. But really, what I want to convey here is the goal here is to have the versatility that you would need to do quantum simulation of a broad range of models. So with this, I just want to acknowledge the people in the lab. I was lucky enough to get a very talented group of people that are now in the lab trying to make this work. And with this, thank you. I'm happy to take questions.